YouTube analytics suggests that people's attention span is a lot less than the length of my videos. In other words, my videos are too long. But how can you fully cover a topic by spitting words like a machine gun? My videos take as long as they need to take, I'm sorry. Anyway, you'll be pleased to know that this is the final type of light that I shall be reverse engineering. It's a 30 lead unit, looking pretty much the same as the one in my previous two videos, except that this one has a night light function where it lights dimly at night and it brights when the PIR detects movement. The circuit is broadly similar to the other two, with a few minor differences. For example, this one has a 3.3 volt regulator, as opposed to 3 volts in the previous one, and 2.8 volts in the one before that. And note they haven't fitted a capacitor on the input. This is just cheapness. On this one, the FET, notice I've learnt how to draw FETs now. The FET has a pull-down resistor, but it has no series resistor. And one of the previous ones had a series resistor, but no pull-down, and the one before that had a series and a pull-down. So they're all different. And on this one, pin 6 is pulled down through a 0-ohm resistor to the ground instead of being biased at 0.8 volts or just left open circuit like in the previous one. So how does it work? Well, the solar panel over here charges through the Schottky diode the 18650 lithium cell. The charge can be up to 45 milliamps in the sun, 10 milliamps on a white sky, or 5 milliamps on a blue sky. There's no overcharge protection at all on these things. The regulator provides 3.3 volt to the chip and to the PIR sensor. The chip appears to be an SW03 series. One of the previous ones is marked SW03BS Bravo Sierra, but there seems to be a series of these chips. This one may be different. It's certainly got the same pin out, and I think this pin here determines what mode it's in. So I can't be sure, but I think it's an SW03BS. In daylight, the CDS pin here is held up at around about 2 volts by this voltage divider and the solar cell, and that inhibits all of the rest of the function of the thing. At night, this pin drops to 0 volts. And that enables the PIR and nightlight functions. In nightlight mode, as soon as it goes dark, this pin here starts pulsing up and down rapidly at 15 kilohertz with very short duty cycle, and that pulses this LED, the LED panel, on and off very quickly. So the average current for that is 3.3 milliamps. If the PIR sensor senses any disturbance in the PIR, in the infrared, it raises the voltage on this pin. The capacitor here is just to absorb transients and stuff like that. That pin goes high or higher. There's some logic in there that controls things such as the daylight inhibit, and then it drives that pin high, and it pulls that, it just pushes that, turns that MOSFET hard on, and in that mode it appears to take 108 milliamps on full brightness. After 20 seconds, if there's no more disturbance on the PIR, this will switch back to nightlight mode. That's pretty much it, really. It's obviously designed for sunny climes, because in a British 12-hour winter night, this would consume 39 milliamp hours, which is about all it would receive on a winter's day from the sunlight. So it would just about scrape through the night on what it receives during the day, as long as it didn't get triggered. If it got triggered, I reckon this would go flat. So maybe it might be okay in China or California, but not so much in northern climes. Anyway, if you like this, give me a thumbs up, and I promise that will be the last one that I'll reverse engineer. I might make a few more comments, but I'm not going to reverse engineer any more of these. Bye.